molecules that, like here, polyols, or aldehydes and ketones and acids that have a high content of oxygen. And the new processes are required effectively to upgrade these materials. And for instance, aqueous phase hydrodeoxygenation on transition metal catalysts. So that's why we're interested in these transition metal and water interactions. So the idea is that we have very highly complex reaction networks if we want to upgrade the biomass feedstock. So we start, for instance, with compounds here like sugars. And there are dehydrogenation and dehydration reactions, hydrogenation reactions that can happen, for instance, from going from here to here, dehydration reactions in order to get to gasoline range products that can be used as fuels or also as base chemicals for the chemical industry. And in order to do that, we need to optimize catalysts, so both the catalyst and the reaction conditions. And of course, this can be done experimentally, but computer simulations potentially can significantly cut the costs of these experimental catalyst optimization. Now, the problem is that it's a daunting task to deal with the complexities that are involved because we have very big reaction networks. There are a lot of reactions that can happen, and taking all of this into account is very complex. For instance, if you look here, this plot here is showing that the order of magnitude of possible reactions and intermediates of those reactions if you increase the carbon numbers within a sugar. So if you go from 1 to 6, you have like, you go into the millions of different possibilities that in principle you have to consider when you look at these reaction networks. And there's of course an influence of the solvent. And reactions take place not only in the liquid, but at the liquid-solid interface. And the key point is that, of course, for precise simulations, ab initio or density functional theory, it's out of reach to go either look at the timescales that are required to sample all these reactions, and of course, it's not feasible to look at all those reactions. So instead, the idea that we have, and probably a lot of other people are following, is that instead we are using a multi-level and a multi-scale simulation approach, where we use basically linear free energy relations to, or let's look at here, so group additivity methods to estimate the thermochemistry of a reaction. And those are parameterized against QM-DFT reference data. And for those, we need a large set of conformations of reactants, intermediates, and products to compute the reference data. And then we can parameterize these group additivity methods. And so-called BEP, Brønsted, Einstein, Polanski, linear free energy relations to estimate reaction barriers. When we can do that, we can do microkinetic and reaction network modeling so that we can predict which of all those millions of, or tens of thousands to millions of reactions and intermediates are actually the important ones. Then we can use high-level simulations, for instance, adaptive QMMM type of simulations that mix quantum mechanical modeling and classical modeling for the larger environment to refine barriers of important reaction steps and look at explicit reaction mechanisms to determine which changes, for instance, to reaction conditions, solvents, and or catalysts can positively influence the reaction network to create products that we are interested in, right? Now, in order to do this and get idea about influence of the solvent, there's a good question, how do we study the influence of the solvent, right? Because, I mean, here for reference data, what you can do is you have a metal surface and then you stick your reactant on it in a product. But of course, there's no sampling involved. We don't know what the conformations are. We don't know how the solvent influences the conformations that we have to input basically into our reference QM data calculations for these approximate methods here. So what we need is an efficient force field to describe the solid-liquid interface. And that's effectively what I want to talk about today. I have some more information here why water has an essential role. And in principle, so in practice, actually, water can modify the catalytic activity. So I'm showing here two examples. Maybe we want to focus on this one here, the livolinic acid, which is represented here. The conversion into gamma-valorolactone, GVL, which is depicted here, by metallic-supported catalysts. So, for instance, in this case with the ruthenium, it has been shown that it was a collaborator that has shown this, so Karine Michel, that water activates the ketone hydrogenation, right? So here you have the conversion in THF, and if you go to water solvent, suddenly you get a very high conversion and yield as well. There's also an effect in platinum, but on platinum for this specific case it's not as pronounced, right? But you can't know this a priori. So it would be very useful actually to have a way to look at these solvation effects. And here is another example where we see, for instance, with density functional theory calculations of the hydrogenation of acetone and ruthenium as an example, that if you don't include a solvent, the energetic span, so that's the span along all the reaction steps from the lowest to the highest intermediates, is 1.37 electron volts. And if you use a continuum solvent model, which is the most simple approximation that you can do, and it often works well, but in this case the prediction would be that, well, there's no effect of water. So if you put it just with a dielectric that has the same dielectric as water. Now, if you add water molecules explicitly to the calculations, for instance, 1 here, a 3, 11, and then the question is like in which conformations they are and how to sample the relevant conformations, you get effects. You can see that the effect is actually on the order of like 30% of the energetic span of that reaction. So water is actually important. And performing ab initio MD simulations is not really possible. So this is, I mentioned this before, it's very expensive. So this is an example here where we have a bulk platinum system and with a 12 angstrom layer of water. So it's not a lot. It's actually a quite small simulation system if you think about it. Nevertheless, if you want to do density functional theory molecular dynamics simulations with a simple GGA functional, so that's one of the cheaper ones that are affordable and also useful actually to converge the electronic structure of the metal using a 1 femtosecond time step. If you run this on, say, 64 CPU cores, as far as I know, well, there are new methods now, but I mean, what we looked at here like 2 years ago, there were no reasonable methods actually that scaled effectively to very large core counts, so you can't really speed up the simulations, but what we get is basically 150 steps per day. So you wait a day, you get 150 femtoseconds of simulations. So if you want to simulate, say, 10 picoseconds, you have to wait 2 months, so it's computationally expensive. So our objective here is to develop a force field that is capable of describing the solid-liquid interface, and particular interest is platinum because it is an efficient hydrodeoxygenation catalyst system. And what I'm going to focus on here today is platinum water, but of course we want to extend this to platinum polyalcohols and carbohydrates eventually. And what we want to do with this is being able to generate an ensemble of relevant adsorbate conformations. And the other thing that we can do, of course, if we have an approximate reaction pathway, we can estimate the solvation-free energies along the reaction path from so-called free energy perturbation calculations. So we could basically get the vacuum absorption energy from DFT, and then via free energy perturbation, so approximately at the solvent effects along the reaction coordinate. So how do we develop a force field that may be useful? First, we look into the literature. What do people do? And people do very simple things sometimes. So there's a work by Heinz that just uses a Lennard-Jones potential to model the interaction between water and the metal surfaces. This has an advantage that there are no code changes required effectively, unless, for instance, here you have a modified repulsive term in a modified so-called, well, basically a modified Lennard-Jones potential. And there are parameters available for several FCC metals, including platinum, and you get the rest of the parameters by regular Lennard-Jones mixing rules for different atom types. So you can run simulations with that. But is it any useful? Well, obviously, this is far from accurate and has not much in common with a real platinum surface, right? So for instance, for water, if you use a force field like this, the adsorption is predicted on the hollow sides, right? So if you look at the surface of the platinum, so not on the top of the atoms, but in between. And it gives you the wrong adsorption layer structure. Chemisorption is fully ignored, so there are random orientations of the adsorbed water molecule, while in reality there is some sort of chemical bond that forms. There's a real chemisorption of water and platinum. What about an explicit chemisorption potential then? So there have been previous efforts, and for instance, Stillinger-Weber-like potential was developed by Siepmann and Sprigg in the 90s, where you have a repulsive term between platinum and oxygen atoms, dispersion contribution, of course, and then here a term that depends on the platinum water orientation. So this contains the dipole moment of the water molecule and the platinum, so it helps orienting the water molecules on the surface. That accounts for chemical binding, and then a three-body term, where you have a term that takes into account 2 platinum atoms and an oxygen that helps push it on top of the platinum atoms. So this exists, and it also includes electrostatic induction terms, but it has been parameterized a long time ago, and it also would be difficult, I think, to extend to other carbohydrates, for instance, or it would be a lot of work. So what I wanted to show here is effectively, if you look at this table here, so we have top sites, bridge sites, and then 2 different types of hollow sites. The adsorption energies here, it qualitatively correctly describes the adsorption, with the top side being preferred here over the other sides, as you can see. And the adsorption is via the oxygen atom and not via hydrogen atoms. That's also correct. So the problem is that this is not easy to extend to carbohydrates. And it's an older parameterization. It could be reparameterized. But instead, we decided to do something by our own and start from scratch. Now, how important is polarization? If you bring the image charge model, so if you bring a charge close to a conductor, you know, from macroscopic physics, of course, there is a so-called image charge interaction. And you know, so you could define a plane on top of your metal and compute this image charge explicitly if you have point charges on a classical force field, for instance. And the problem here is that it's not clear where to put the position of the image plane in such a calculation. And of course, it wouldn't account for atomic details of rough surfaces, right? So for instance, if you want to go at some point to metallic nanoparticles, that wouldn't be possible. So instead, another thing that force field that has been developed in the literature, mostly for gold, that's why it's called GOLP, uses a so-called polarizable rods. This is similar to a Drude oscillator, but instead this is like a Drude rod model, which is employed in the GOLP force field. And that would be also very simple to implement in a classical molecular dynamics code, for instance. And here the atom-wise polarizability is described by a rod that has a fixed length and is characterized basically by its mass and the charge Q and the length of this rod. And then you can compute the interaction-free energy as an average of the electrostatic energy. So on average, it would give you back the polarization energy of the metal. So this is quantitatively correct at long distances. And it's trivially applicable in any MD code, but can we use it for platinum and water? And what we looked at is, for instance, if you put a water molecule on top of a metal surface, and then you rotate, it's like rotating a dipole here, right? What you see here is, so a priori it's not clear. You can choose the 2 charges of this rotating dipole as you wish, plus or minus on platinum, and corresponding opposite charge on the rotating particles. But then you get qualitatively different results. So if you look here at these triangle, the dark blue and the light blue triangle, when you're close to the surface. So when you're far away from the surface, you get qualitatively, of course, the same results. But once you're close, you get these finite size effects. And so that's not very good. So instead, what you can do, what we looked at is basically you symmetrize this rod model where you use you rotate it around the center, and you use a positive and a negative charge at the opposite ends of the rotating rod particles. And I'm sorry, so actually I realize now that there's a lot on this plot going on, but what I want you to focus on here is basically this here is the total interaction energy from density functional theory if you rotate that water molecule. And the electrostatic interaction energy that you get from this rod model is what you can see here. So it is a rather small contribution, right? So first of all, if you use a non-symmetric model, you get qualitatively wrong results depending, or you don't know, yeah, you would have to basically shrink the rod to a very small distances, and then it becomes numerically unstable. But if you use the symmetric rod, it's actually qualitatively correct. The problem is that we think it's not worth the effort because you see the adsorption energy, and it's just really a tiny contribution to the total adsorption energy because we have a very strong chemisorption in the case of platinum. So with all this knowledge, starting what we did is we wanted to have a computationally efficient force field for platinum-water interaction, something that's easy to implement as well. Computationally cheap, easy to implement, and then extensible to polyalcohols. And so what we parameterized is a potential that contains a Lennard-Jones term that models basically the dispersion interaction and part of the chemisorption repulsion at short distances, augmented by a Gaussian potential here that corrects the, and I'll show a little bit more about this, the corrugation of the surface potential, and an angular term that corrects for the orientation of the water molecule on the surface.
May I ask a question?
Yes, please.
How do you enter water?
How do I?
Enter the water.
Yes.
How is it?
I will. The water, so let me go one step back. So what we want to do is we want to do atomistic simulations with classical force fields that have basically a pairwise additive expression where we have point charges on, so fixed bond lengths and point charges on a triangular water molecule, the most simple things that we can do. So it's an explicit representation of water. And we don't exclude explicitly the electrostatics and somehow fold this into the overall fits because this is never going to be very accurate with the simple forms that we have here. And as we have seen, the electrostatics accounts for less than 10% of the adsorption energy. So we have this Lennard-Jones potential. What we do, so if you look at the surface here, the blue dots or the blue ball spheres are platinum sites. We add virtual sites basically at all the hollow sites, so in between the platinum atoms at the surface. Because if you do that and you use a potential like this, it drives the adsorption on top of the platinum. The problem is now that the attraction at the hollow sites and the bridge sites is too strong. In other words, that the corrugation of the surface potential is not strong enough. So what we did is augment this with the repulsive Gaussian functions sitting at the virtual sites that basically pushes the water a little bit away from the virtual sites. And that's the form of just the repulsive Gaussian function. It is polarized in terms, so we have it, of course, in the x and the y direction. It has the same extent, and then it's a little bit oblong along the z-axis, perpendicular to the surface. Of course, you could do the opposite. You could put the Lennard-Jones potentials on the platinum atoms, and then instead of a repulsive potential, you would have to actually have an attractive Gaussian situated at the platinum atoms so that you get the adsorption on the top sides. We did both, but in order not to confuse, I'll just focus on this potential here. Then, okay, so the videos are playing. We need an angular correction. So if you think about a water molecule, so here a water molecule is depicted, and you can see when you put it on a surface, so if it's adsorbed here on the surface, you have the so-called cartwheel angle because the water molecule, it can bend down and up. And you have the propeller angle, it can rotate this way, the water molecule, and it can rotate in the surface. So this helicopter rotation actually there's no isoenergetic, so it doesn't, there's no distinction between the orientation in terms of energetics. But of course, propeller angle, so once you start getting pushing the hydrogen atoms into the surface, there's a repulsion, as you can see here, right? So that's from DFT reference calculations here. And the cartwheel angle here as well. The water absorption on platinum-111, the minimum is actually the water is planar to the surface, the orientation. So you have a minimum here around 90 degrees. And if you push the water up or down, the energy goes up, of course. Here you have the repulsion when you push into the water, but also, the water pointing up is also energetically less favorable. And what we do here is we have an angular correction where we have for the cartwheel and the propeller term in terms of so we switch it off at longer distances, of course, right? So we don't want to have an influence of the water orientation once it's back in bulk, only when it's close to the surface. And then we use here a truncated Fourier series for the cartwheel angle and a simple repulsion here with an R to the 5 term that turned out to work reasonably well for that just depends on the distance of the hydrogen atoms to the surface. And how well does it work? So it was fitted to approximately 200 adsorption energies of a single water molecule to the surface. And here's a correlation plot for approximately 800 adsorption geometries. What I want to show here on the left-hand side, so on the top, you see very repulsive and also attractive energies. Of course, the attractive energies here are the most important ones as well. So that's a zoom, basically, of the top plot. On the left-hand side is the fit of the force field. On the right-hand side, what you see is, in blue, is this simple Lennard-Jones potential by Heinz. You can see that basically there's no correlation with any real adsorption on the platinum surface. QMMM and ICQMMM is using density function theory for the water molecules, and then the Siepmann-Sprigg potential for the interaction with the platinum surface, either without, so the QMMM, or with this image charge term by Siepmann and Sprigg. And you can see that also fails spectacularly, so it doesn't work very well. So actually the simple force field is better than the most complex models that we have otherwise available, apart from going to a full DFT calculation. The angular adsorption profile, again, on the left-hand side, you see the fit of the force field. And on the right-hand side, you see the Heinz model in blue, the QMMM model with and without image charge model. And I think we get a pretty reasonable fit for the energetics, while there's no effect for the propeller angle, because the Siepmann-Sprigg potential here, the QMMM model, only takes into account the dipole moment of the water molecule, but it doesn't care whether it rotates or not. So clearly that's also better. How does the adsorption profile look like? So if you take a water molecule and you bring it closer to the surface on top sides, so where it's the optimum absorption, or on the bridge sides, it looks pretty good. It looks better for the force field than for these other models. We have a good profile, in particular on the top sides, where the adsorption is stronger. There's a little bit of overbinding, as you can see here, on the hollow sides. So to guide you through these plots, the solid lines here, the black is the DFT reference, and here blue is red is the force field, and the solid line is the top sides, and the dashed lines are the two different hollow sides, hollow and bridge sides. So the adsorption profile is really good on top sides. We have a little bit of overbinding on hollow sides, but surface corrugation is somewhat too low, but it actually looks pretty reasonable. And as a first evaluation of the test also, because everything has been fitted to a single water molecule, now if you want to do a MD simulation with a classical force field, you have a water model, you choose a water model, so we have tested different water models from tip 3P to tip 4P, EW, tip 5P, OPC, and SPCE. And here's a correlation plot of the density function theory adsorption energies versus the force field that we have fitted for the interactions between water and the surface, and different water models for the water-water interactions. And here, of course, again with QMMM calculations. And you can see that we get a reasonable correlation. So I should say, so these are, adsorption energies for defective ice layers, where we have started with an ice layer. So it's a little bit hard to see, but you see these hexagons here. So there's these 6-membered rings that form on the surface actually when you have ice on platinum. And you can remove water molecules, and we have created a lot of different structures and optimized them that have different defects. And those are the two different energies that you see here. So what we see here is basically that one of these water models, this OPC model, which is actually a relatively new parameterization, overestimates the water-water binding energies. And all the other models underbind a little bit. And I think, well, obviously, one thing that we are missing are many body effects between water molecules and water molecules mediated through platinum. And that's missing, and that's something that we can't just get simply in there with a simple pairwise additive force field. But other than that, it looks actually reasonably well. And going to an application, so I'm not sure a video should start here. I'm close to the end of my talk. We have looked actually at the hydration of the platinum 111 surface, doing ab initio molecular dynamics simulations of platinum surface with water, and then also simulations with our new force field using a TIP3P water model here in red. And then the Heinz simple Lennard-Jones interactions, and with the QMM models using DFT for the water molecules only, and then the Siepmann-Sprigg potential for the interactions. So I don't know. I think the video, is not starting the video. Sorry for that, but can believe me, it works. So you would see actually something moving around. And going back to your question, so that's a fully atomistic simulations with a simple TIP3P water model for all the water molecules. And what we see here is the density profile. So it's basically the water density at different distances, so different points of layers basically of water here above the platinum surface. So we have a strongly bound adsorption layer. So black here is the DFT reference. So we have a little bit of overbinding actually in that region. But it follows pretty well actually the DFT curve, also going moving further away from the surface. Now there's one caveat, is that the simulations are probably not fully converged, simply because we don't have enough sampling with the density functional theory reference calculations. While with the force field it will be easier and simple, would be simple just on a simple laptop you can run the simulations, right? And then here you see site occupancies, and you can see that with site occupancy I mean whether the water molecules on the surface are sitting on top of the right sites, and the distribution is correct, whether they are on top of the platinum atoms or in between. And you see that our force field here actually reproduces the DFT data pretty well, while the Siepmann-Sprigg potential puts all the water molecules on the top sides, which is wrong with these ICQMM models here. And the Heinz model has actually no structure whatsoever on the surface, obviously. Which is completely wrong. So that brings me to the end of my talk. So basically what I've shown is that if you want to include the image charge effect with the rod model, you have to make it symmetric. I didn't go very much into details here. That should be obvious, but people have not been doing this in the past and still used it. But that should be done if you want to use such a rod model for the electrostatic interactions between a solute or, well, basically adsorbates and your metal surface. Then the electrostatics and water adsorption in platinum 111 is only a small fraction, so you can